Alright, we'll be looking at escape velocity, and this is an aspect of gravitational field in physics. They said escape velocity is defined as the minimum velocity required for an object, example satellite or rocket, to escape or leave the gravitational influence or field of an astronomical body, example the Earth, permanently. So escape velocity is the velocity with which the satellite moves around the Earth. Okay, so we're having something like this, and then this is the Earth. That's the diagram of the Earth over there. Okay, and then we have a satellite that is orbiting the Earth. The satellite is orbiting the Earth. This shows us the orbit. The satellite is orbiting the Earth. Okay, that's revolving around it. And you see the escape velocity here. It tells us that at some point it will move tangentially. This is at a tangent. The escape velocity moves at a tangent. It escapes from the Earth's gravitational influence. Okay, so that is it. The escape velocity moving tangentially, escaping from the gravitational influence of the Earth. Okay, now how do we prove the formula? How do we obtain the formula for escape velocity? So recall that from Newton's law of universal gravitation, that F is equals to G m1 m2 over r square. Okay, so if you say let m1 be equals to me and m2 be equals to m. That is, say let m1 be the mass of the Earth and m2 be the mass of a satellite. So I'll then place it inside here. The formula now changes to F equals to G me m over r square. Okay, alright, so we are having the force as this. G is the gravitational constant, me mass of the Earth, m over r square. R is the radius, okay, or distance apart. Okay, so it says the work done, you can call this one equation 1. Now it says the work done in moving a unit mass m from a point towards the center of the Earth at a distance r is W equals to F times R. Okay, so we know that work is force times distance. Work is force times distance. Okay, right? So the work done in moving a unit mass m from a point towards the center of the Earth at a distance r is given as W equals to F times R. I know that work is force times distance. Now, if I substitute, we call this equation 2. I say substitute equation 1 into equation 2. Substitute equation 1 into equation 2. I'll be having that W is equals to, in place of F, I write G me m over r square multiplied by my radius r times r. Okay, so this, we key one of this, and I have that W is equals to G me m over r. Okay, so the work done is G MEM over R. Alright, so at this point we'll call this equation 3. Okay, my work done is given as this. Also recall that kinetic energy is equals to half mv square. Okay, and since we are looking at escape velocity which is VE, then permit me to change this to VE. You see, if V is equals to VE, it means that my kinetic energy will be equals to half mve square. Okay, now I will equate the both of them. If I call this one equation 4, I say equate 3 to 4. Alright, equate equation 3 to 4, and that means that you are equating work done to kinetic energy. That is, we are equating work done to kinetic energy, or you say equating kinetic energy to work done. That is, kinetic energy equals to work done. So that would be kinetic energy now is half mve square is equals to my work done is g MEM over R. Okay, so I equate equation 4 to equation 3. Equation 3 is this. Okay, so I equate the two of them, and you see that M will cancel out M. Alright, so I'll be having what? VE square over 2 is equals to G ME over R. Okay, so I'll cross multiply, and I'll have that V E square will be equals to 2 GME over R. That's when I cross multiply this, 2 will multiply this. Okay, and then take square root of both sides. This is VE square all raised to power half equals to 2 GME over R raised to the power of half. Okay, so 2 will eliminate 2, and VE will be equals to the square root of 2 GME over R. Okay, so we have this. It means that okay, you can say let ME be equals to M, mass of the earth, and R is equals to capital R, radius of the earth. That's mass of the earth, and this is radius of the earth. So this now will be escape velocity will be square root of 2gm over r. That's the first formula for escape velocity. The first formula is root of 2gm over r. Okay, so we continue. Say but my escape velocity is the square root of 2 capital G me over r, isn't it? Okay, then the next thing I say recall that acceleration due to gravity is equal to G me over r square. Okay, all right, that is G equals to force per unit mass. When you put that one there, that G is capital G MEM over r square divided by m. So that's G MEM over r square times 1 over m. This we cancel out this, and be having that G is GME over r square. So you come back here that acceleration into gravity is GME over r square. I'll place it back. I'll make ME subject to formula. If I cross multiply, so if I cross multiply now, we're having GME equals to GR square. Okay, so divide by the coefficient of ME. I have that ME will be equals to GR square divided by G. Alright, so ME is this, so I can then substitute into this equation. So if ME is GR square over this, or substituting to this equation, say it then means that, say by substituting ME equals to GR square over G, I'll be having that V, escape velocity, is the square root of 2G times GR square over G divided by R. Okay, so I'm having this as my escape velocity is this. So then R we cancel out one of this, and G we cancel out one of this, right? Okay, so let's make it more professional. So this is VE equals to square root of 2G times GR square over G times 1 over R, right? So this will eliminate one of this, and G will cancel G. So I'll be having that escape velocity is the square root of 2GR. Okay, since this has eliminated, so I'm having 2GR. So therefore, escape velocity will be the square root of 2G capital R. This is the second formula for my escape velocity. So the second formula for escape velocity is V equals to square root of 2GR, and then G is acceleration into gravity, R is the radius of the Earth, V is the escape velocity. While the first formula I had was V equals to square root of 2GM over capital R. Capital G is the gravitational constant, which is 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. M is the mass of the Earth, and R is the radius of the Earth. VE is the escape velocity. Alright, so we'll be making use of these formulas. So take note of these two formulas. Okay, the first example says calculate the escape velocity of a satellite from the Earth's gravitational field. We are given acceleration due to gravity as 9.8 meters per second square. The radius of the Earth as 6.4 times 10 raised to the power 6 meters. Okay, so we list the parameters out. First thing that was given to us there was acceleration into gravity. So given that G is 9.8 meters per second square, and then the radius of the Earth is 6.4 times 10 raised to the power 6 meters. Okay, so we then look for the escape velocity. My escape velocity is VE equal to square root of 2GR. Okay, so if I substitute, by substitution, I have that VE is equals to the square root of 2 times 9.8 times 6.4 exponent 6. Now we're having VE as the square root of, so when I multiply this, it gives me 125,440,000. Okay, and the square root now will be, so square root of this is equal to, square root of this gives me 11,200 meters per second. Okay, so that is my escape velocity, 11,200 meters per second. You can convert to standard form. This is, if you move, that's 1, 2, 3, 4. That's 1.12 times 10 raised to the power 4 meters per second. It's my escape velocity. Okay. Alright, we have a second question on the board. It says complete the following table assuming Newton's law of universal gravitation, and we are given the gravitational constant as 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. The table shows us 3 planets, specifically planet A, planet B, and planet C. And then we observe that on this other column we have the mass, the diameter, the weight of 10 kg ball, and finally the escape velocity. Our duty is to fill up this table, to fill up the empty spaces. Alright, so we'll consider that of planet A first. Consider planet A. Say for planet A, for planet A, first thing you take is the mass. The mass of planet A is say the mass m is equal to 2.0 times 10 raised to power 27 kg. Then we'll also take the diameter. Diameter is given to us as 1.84 times 10 raised to power 8 meter. Okay, so you look for the radius. The radius now, so your radius r is diameter over 2. That's half of the diameter, which is 1.84 times 10 raised to power 8 divided by 2. Okay, so my radius r will be equal to, so my radius will be 9.2 times 10 raised to power 7 meter. Okay, so the radius is 9.2 times 10 raised to power 7. When you divide this, because the radius is half of the diameter, and diameter is 2 times the radius. Diameter is 2 times the radius, so radius will be half of diameter. Okay, so that's why we're having our radius as d over 2, which is 1.84 exponent 8 divided by 2. That's this. Okay, now the next thing we'll look at here is the weight of 10 kg ball. Let's find the weight. You see, weight of 10 kg ball on planet A. So we say that weight is equals to mg, isn't it? And the mass of the ball here is the mass of the ball m is 10 kilogram. What we don't have is g, so we are looking for g now. G is unknown, so we say that g is acceleration due to gravity is g m over r square. Okay, and the m here in this case, the m in this case is not this. All right, m in this case is this other one that is given to us. This one given to us as 2.0 times 10 raised to power 27. So we'll write it down. So this now will be equals to g equal to 6.67 times 10 raised to power minus 11. Okay, so let's avoid confusion. Let's represent this as MP. That's mass of the planet, and call it MP, mass of the planet. Okay, so that would be times 2.0 times 10 raised to power 27 divided by my R there is 9.2 times 10 raised to power 7 all raised to power 2. Okay, so now g, acceleration to gravity, will be, if I multiply here, this gives me 1.337 times times 10 raised to power 14. Okay, I think it's times 10 raised to power 17 rather, times 10 raised to power 17, and then when I take the square of this, it will be, okay, that gives me 8.464 times 10 raised to power 15. Okay, so when I divide it now, g, if I divide these two, I'll be having, if I divide the two of them, I have, okay, so when I divide these two, it will give me 15.76 meters per second square. That's the acceleration due to gravity on that planet. The acceleration due to gravity on that planet is 15.76 meters per second square. Okay, so that is it. Now, hence we have gotten the value of acceleration due to gravity of that planet. We can then place it into this equation so that we can find the weight of the ball, the weight of the 10 kg ball. So place it inside there, and then, okay, and so we say that W is equals to mg, and then the mass of the ball is 10 kilogram multiplied by, we had g as 15.76, so that is 15.76 meters per second square. If I multiply them now, I'll be having my weight as 157.6 Newton. Alright, that is the weight of the 10 kg ball. When I multiply this and this, I have 157.6 Newton. Okay, so the next thing they say we should solve here is the escape velocity. It's the escape velocity. So the escape velocity now, you see escape velocity VE. I'll use the second formula. V is equals to square root of 2GR. Okay, and then we'll take that, say VE will be square root of 2 times the value of small g is 9.8. Small g, we had small g, the acceleration due to gravity on that planet, we had it as 15.76. Okay, that is 15.76 multiplied by the radius of that planet, capital R, is 9.2 exponent 7. That is 9.2 exponent 7. So I'll be having, when I multiply now, I'll have VE as the square root of so I have 2899, and that's 840,000. Okay, that is it. Okay, that's 2899 840,000. And if I take the square root now